what a Reimann sum is an estimate of an area using known shapes. Like the most commonly used ones are rectangles and triangles. Sorry, rectangles and trapezoids. So, all right, well, let's look at this. Coal gas is produced at a gas plant. Pollutants in the gas are removed by scrubbers, which become less and less efficient as time goes on. The following measurements made at the start of each month show the rate at which the pollutants are escaping in the gas. Okay, so at time 0, the rate at which they're escaping is 5 tons per month. But then after 1 month, the rate that's escaping is 7 tons per month, and it continues to increase from there. Make an overestimate and an underestimate of the total quantity of pollutants that escaped during the first month. All right, well, let's start with the underestimate. Any suggestions as to how many pounds or tons of pollutants escaped during that first month? What would an underestimate be? Time is starting at 0, and your first month ends at 1 on the chart. So the underestimate, Celeste, would be 5, right? Because at the beginning of that month, only 5 tons per month are escaping. So the underestimate would be 5. The overestimate would be 7, right? Because at the end of the month, that's how many are escaping per month. So the exact amount over that month is somewhere between 5 and 7. All right. Now we're going to make an overestimate and an underestimate of the total quantity of pollutants that escaped during the first 6 months. The easiest way to do this is to graph this data. So let me get a new slide here. And your graph doesn't have to be absolutely perfect, but let's just kind of graph the data. All right, now what I'm going to do is I'm going to just lightly connect these dots with kind of a smooth curve. Let's just talk about month 1. Our underestimate was that 5 tons per month escaped. What would an underestimate during the second month be? 7. Good. And really, the way that we're getting 5 and 7 is we're multiplying the length of 1 month, so 1 times the smallest amount, or the amount that's escaping at the beginning of that month. What would an underestimate for the third month be? 8. Okay, so what I'm doing is I'm drawing rectangles here. Yes, I would use... You can either use your pencil or one of the colors right here. All right, so our underestimate is going to be 5 plus 7 plus 8 plus 10 plus 13 plus 16. Do I need to add 20 to that underestimate? No, because that's basically 6 months worth. I've added up 6 different ones. All right, and when you add those numbers together, you get 74. What are the units here? Tons of pollutants. Good. And we can just go ahead and say tons. Okay. One other thing I want to point out, on the x-axis, this represents months. What's the units on the y-axis? Tons per month. Good. So when you multiply months times tons per month, your months cancel. Think about finding the area of each one of these rectangles. The area of each one of these rectangles is 1 month times however many tons per month. So that's where your months will cancel. Okay, an overestimate. Eddie? Oh, sorry. Okay. The underestimate's 59. Sorry, I looked on my notes from last year. Must have looked at the other one. Okay, let's talk about the overestimate. Switch colors here. What was the overestimate for the first month? 7. What would the overestimate for the second month be? 8, right, because at that second month, the beginning is 7, but the end of it is 8. So the overestimate would be the 8. For the third month, it would be 10. Good. And then 13. 16. And what would the overestimate for the last month be? 20. Good. If I look at the green graph that I have up here, then the underestimate for the first month would be the amount that's escaping at the beginning of the month, and the overestimate would be the amount that's escaping at the end of the month. Well, because we want how much is escaping over a 6-month time period, not just over 1 month. So I need to add up 6 months. All right, so I'd be adding 7 plus 8 plus 10 plus 13 plus 16 plus 20. And hopefully that equals 74 tons. Type it into your calculator. Okay, now there's some things I want to point out here. On your graph, as if you look at the my blue rectangles, those blue rectangles, are all of those underneath my green line or above my green line? Underneath. So that makes sense that it's an underestimate. And all of the red rectangles are above that green line, so it's an overestimate. Also, if you'll look at your table up here, because the amount of pollutants is increasing, or the rate of the amount of pollutants is increasing, when I made my underestimate, I used all of the values in the table except the last y value. But for my overestimate, I skipped the first value and then used the rest of them. So there's kind of a pattern going on there. Riley? Yes, you can definitely use a Riemann sum on a decreasing graph also. So if the graph was decreasing and you wanted to make an underestimate, do you think you would leave off the first one or the last one? The last one. Good. If your graph is decreasing, then your overestimates would be like, oh, I'm sorry, I said underestimates at the beginning. Sorry, we'll talk about overestimates since I've already drawn it. All right, so if your graph is decreasing, then your overestimates, you're going to use the first one, but not the last one. We're going to get let me talk a little bit more about that in a minute. All right, let's go to part C. Using the answers to part B, make an even better estimate of the total quantity of pollutants that escapes during the first 6 months. What could we do? Average them, absolutely. If we know we have an estimate that's too low and we have an estimate that's too high, then a better estimate would just be to average them. So 59 plus 74 divided by 2 is 66.5 tons. Now, is that an exact answer? No. It's just I know that I have a number that's too small and one that's too big, so if I average them, it will be closer. Okay, part D brings in another part of new vocabulary. In this problem, the overestimate is also called the right side estimate, and that is because on your overestimate, and that's my red rectangles here, what side of my rectangles is the green curve hitting on the red rectangles? The right side. So my overestimate is considered a right side estimate because the curve is hitting the right side of those rectangles. So up here on the overestimate, you might put right. Okay, we'll talk if the graph is decreasing, then we'll talk about that in just a second. But right now, for this particular graph, the overestimate is also called the right side estimate. The underestimate could also be called what? The left, because if you will look at my blue rectangles, the green curve hits the left side of each of those rectangles. All right, however, y'all are a step ahead of me. If the graph is decreasing, okay, so you've got a graph that's decreasing. Is this an over or an underestimate? That would be an overestimate. And what side of the rectangles is my line hitting? The left. So for a decreasing graph, the overestimate is also the left estimate. But, the underestimate, which I've drawn in purple, the curve is hitting the right side of those rectangles, so it's a right estimate. So you may be asked to either give an overestimate or an underestimate, or a left estimate or a right estimate, and you have to figure out which one it's supposed to be. Over or under probably is more simple, but they will use left and right on the AP exam. What, Eddie? It depends upon the graph. And really, it's not something that I memorize. I'll draw my graph and then draw over estimates and figure out if it's the left or the right side. So I don't have memorized that for a decreasing graph, the overestimate is the left and the under is the right. I'm going to draw it and kind of work my way through it. All right, you jump out of an airplane. Woohoo! Before your parachute opens, you fall faster and faster, but your acceleration decreases as you fall because of air resistance. The table below gives your acceleration in meters per second squared after t seconds. Given upper and lower estimates of your speed at t equals 10. Okay, now how on earth can we get from time and acceleration to speed? Right, if you were to multiply the acceleration by time, which remember acceleration is meters per second squared, and then you multiply that times seconds, your units are going to be meters per second, which is a velocity unit. Okay, so your x-axis is seconds, and this is meters per second squared. So if you have velocity, if you multiply your velocity times your time, you're going to get acceleration. I'm sorry, if you multiply your acceleration times your time, you're going to get velocity. Okay, once again, let's do a quick graph of this. Okay, so once again, I'm going to just lightly connect my dots. Didn't do that very well, sorry. All right, with your two different colored markers, I would like for you to draw in the rectangles associated with the over and the under estimates. So just draw in the rectangles associated with the under and the over estimates. And pretty soon, some of you are going to be able to do this without drawing the graph. And unless it specifically tells you to draw the graph, I'm okay with you doing it without drawing the graph. A lot of you are going to need to draw the graph. I kind of need to draw the graph. So don't feel bad. So what we're doing here is we're going to add up the areas of all of these rectangles. So what we're doing here is we're going to add up the areas of all of these rectangles. What's the width of every single rectangle here? 2. So I'm going to multiply 2 times each of the heights. Or I could do 2 and then parenthesis and add up all the heights. Y'all okay with that? Yeah. Why write or type into your calculator more than you need to? All right. What is the height of the first underestimate? What's the height of the first underestimate? Okay, 8.03. And then the next one is 6.53, 5.38, 4.41, and 3.61. And if you type this into your calculator, you should get 55.92 meters per second. Was this underestimate a right side or a left side estimate? Good. It was a right side estimate because the green curve that I've drawn is hitting the rectangles of my lower estimate on the right side. Okay, the overestimate. Don't forget your 2 because the width of every single rectangle is 2. What's the height of the first overestimate rectangle? Good, 9.81. 8.03, 6.53, 5.38, 4.41. Do I go on or stop? Good, I stopped. And then this is also a left estimate. And it's 68.32 meters per second. Notice that for my underestimate, the heights of my rectangles, I skipped the first height and then used the rest of them in the table. On the overestimate, I started with the first one but left off the last one. All right, part B is to give a new estimate by taking the average of your upper and your lower estimates. And that turns out to be 62.12. Well, since it says 9.81 instead of 9.810, then that means it's exactly 9.81. So it is considered accurate to 3 decimals. It's just we didn't need that third decimal. Okay, part C, use the trapezoid method to estimate your speed at t equals 10. Okay, so the speed at t equals 10 using the trapezoid. Hopefully you can use your pencil here to do this because you don't have a third color. But what I'm going to do is I'm going to make a trapezoid out of every single interval. And if I make a trapezoid, then it's going to look like this. Okay, it's kind of hard to see. So my trapezoids, I can kind of shade it in here. Okay. The area of a trapezoid is 1/2 the height times the sum of the bases. Now the height of your trapezoid is the distance between the 2 parallel sides of the trapezoid. So the width, the height of our trapezoids is the same as the width of these rectangles from the previous problem. So 2. Good. So the height is 2. Now, the sum of the bases is going to be, the first base is going to basically be the height of on the left side, and the second base is going to be the height on the right side. So for that first trapezoid, the first base is 9.81, and the second base is what? 8.03. Okay. And then I have 1/2 times the height again is 2. What would the sum, hold on just a minute, what would the sum of the next two bases be? Okay, plus 6.53, etc. All right, what's going to happen in every single term that I have here that's separated by a plus or a minus? What am I always going to have? Like if I continue to write all this out, good. I'm going to always have a 1/2 times 2. So let's write this in a little bit easier way. So I'm going to do 1/2 times 2. And then I'm just going to add up all the sums of the bases. But what happens to most of these right here, these numbers? Yeah, they're doubled because for the first trapezoid, I'm going to use 9.81 and the 8.03. For the second one, I'm going to use 8.03 and 6.53. For the third one, I'm going to use the 6.53 and that one. So I'm using all of them twice except which one? The first and the last. Good. So I can just do 1/2 times 2 times the first one, and then 2 times all of the middle ones. Sure, you could do 2 and then another set of parentheses and add up all the middle ones if you wanted to. That would be even less to write. And then the last one, I just want to count once, plus 3.61. And at some point, it would be good to write the 1/2 and the 2 just to show that you've considered it. But yes, they do cancel out. So if you want to rewrite the problem after that, it would be okay to leave it off. But at some point, I want to see that 1/2 and the 2. All right, turns out that you get 62.12. Why is that funny? Okay, it's exactly the same as the average of the upper and the lower. But what does this trapezoid do to the two triangles? It cuts them in half, right? So instead of, basically they're going to tell, on the AP exam, they're going to tell you how to do each, like which method to use. Find an upper estimate, find a lower estimate, or use the trapezoid method to find an estimate. But the trapezoid method is the same as finding the upper and the lower and averaging them. Okay, scoot down to part D. What does the concavity of the graph of acceleration tell you about your estimate? And it's not necessarily about this graph of acceleration, but what it tells you about your estimate. And really, I want it to be a trapezoid estimate. All right, I want to draw something that is very obviously concave up. All right, if I were to draw trapezoids on a concave up graph, is my estimate going to be too big or too small? Too big. Good. Oops. Okay, so concave up means your estimate is too big. But concave down when you draw your trapezoid estimate is too small. And once again, that's something that I have not memorized, but I'll just very quickly draw a concave up or concave down and connect 2 points on that to see if my trapezoids are above or below. All right, in order to determine the average temperature for the day, a meteorologist decides to record the temperature at 8 times during the day. She further decides that these recordings do not have to be equally spaced during the day because she does not need to make several readings during those periods when the temperature is not changing much, as well as not wanting to get up in the middle of the night. She decides to make one reading at some time during each of the intervals on the table below. Using a Riemann sum, write a formula for the average temperature for the day. Can I just take the temperatures on the bottom row and add them up and divide by 1, 2, 3, 4, 5, 6, 7, 8? No, why not? Yeah, the time intervals are different. If that was the temperature taken every single hour, then yes, I could do that and find the average temperature, but I can't do that. So for how long was it 42 degrees? 5 hours. So I have to count basically 42 5 times. So 5 times 42. For how long was it 57 degrees? Or on average 57 degrees. Okay, what would the next one be? 2 times 72. And then 4 times 84. 3 times 89. 3 times 75, 2 times 66, and then 3 times 52. All right, will that give me the average temperature? I need to divide by what? 24, right. Because that was, basically I added up all of the temperatures throughout the day, and since they're 24 hours, I need to divide by 24. All right, turns out it's 66 degrees. So the question was, how is this using a Riemann sum? If you were to graph this data, you would be finding the areas of the rectangles. You'd be multiplying time, which is the width of the rectangle, times the temperature, which would be the height. It's not an upper or a lower because she just took the reading at some point during that interval. She didn't tell you, she didn't say that she took it at the beginning of every interval or at the end of every interval. That's a good conclusion. Okay, this one's kind of exciting because we're going to save people's lives. A plane has just crashed 6 minutes after takeoff. There may be survivors, but you must locate the plane quickly without an extensive search. It was traveling due west, and the pilot radioed his speed every minute from takeoff to the time it crashed. Use a trapezoidal Riemann sum to approximate the distance the plane traveled before it crashed. All right, well, if we want to find distance, then what do we need to multiply together? Speed and time. Okay? Now, the only problem here is that the speed is in miles per hour, but the time is in minutes. So we need to make those two units mesh. So let's keep the speed in miles per hour, but what should we make the time be? In hours. So instead of 1 minute, I can think of that as 1/60th of an hour. All right, let's try and do this without graphing it. We're doing a trapezoid. So the area of a trapezoid is 1/2 times the height. Are each of those intervals, time intervals, the same? Yes, it's 1 minute or 1/60th of an hour. So that's the height of each one. And then the sum of the bases. So the sum of the first base is going to be 90. And then what do I need to do with all the middle ones? Multiply by 2. So I'm going to use Laura's method. I'm going to do 2 times 110 plus 125 plus 135 plus 120 plus 100, close my parenthesis, plus 70. And it turns out the plane is 11.167 miles due west.